Hello dears, this is the first part of the lecture of the topic change of variables in multiple integrals. In this lecture, we will be discussing how to change the variables in double integrals. To evaluate a definite integral of the form integral from a to b f of x dx, sometimes we know it is convenient to change the variable x into another variable. That is, if f is continuous on the interval ab and x equal to g of u has a continuous derivative, and dx can be written as dx is g dash of u du, then we can represent this integral, or we can change the variable of this integral, that is integral a to b f of x dx can be expressed as integral from c to d f of g of u into g dash of u du. That means we changed the variable x into the variable u. Okay, where the limits of u, that is c and d, are defined by uh, a equal to g of c and b equal to g of d, because we have the function is x equal to g of u. Okay, so c will be a equal to g of c and b equal to g of d. So to change the variable in a definite integral of a function of one variable, we need a function like this: x is equal to, or we need a function x equal to g of u. Okay, so similarly we can also change the variables in multiple integrals. Okay, so for that, suppose first we consider the change of variables in the double integrals. Okay, so to change variables in the double integral, we need two equations. Actually, here we need one equation in a definite integral of a function of one variable. We need one equation x is equal to g of u to change the variable. Okay, but in the case of double integral, to change the variables, we need two equations such as x is equal to f of uv and y equal to g of u. We know a double integral is of this form: double integral over some r f of x comma y dA. Okay, so to change the variables of this double integral, we need two equations such as x is equal to some f of u and v, and y equal to g of u and v. That is, we are going to change the variables x and y into the variables u and v, right? These two equations, x equal to f of uv and y equal to g of uv, define a transformation or a mapping, and it is denoted by t. So these equations define a transformation or a mapping t from uv plane to xy plane. Okay, from uv plane to xy plane. Okay, അതായത് ഈ ഇക്വേഷൻസ് ഒരു ട്രാൻസ്ഫോർമേഷൻ അല്ലെങ്കിൽ മാപ്പിംഗ് ഡിഫൈൻ ചെയ്യുന്നു ഫ്രം യു വി പ്ലെയിൻ ടു എക്സ് വൈ പ്ലെയിൻ. ദാറ്റ് ഈസ് for any point u naught v naught, for a point, fixed point u naught v naught in uv plane, the point x naught v y naught, that is x naught is equal to f of u naught v naught and y naught is equal to g of u naught v naught. Okay, that x naught y naught is called the image of the point u naught v naught. Okay, that is the image of a point u naught v naught is a point x naught y naught such that x naught equal to f of u naught v naught comma y naught equal to g of u naught v naught. Okay, where u naught v naught is in uv plane and x naught y naught is in xy plane, because the transformation is t is from uv plane to xy plane. Okay, all right. Now before entering to the change of variables in double integrals, we have to discuss a definition, which is Jacobian or Jacobian determinant. Okay, Jacobian or Jacobian determinant. For a transformation t, which is x is equal to f of uv and g equal to g of uv, the Jacobian of that transformation t is denoted by dou of xy divided by dou of uv, and is defined by the determinant dou x by dou u, dou x by dou v, dou y by dou u, dou y by dou v. That is the 2 by 2 determinant. Okay, that is for a transformation t which is x is equal to f of uv, g equal to g of uv. The Jacobian is denoted by this and is defined by dou x by dou u, dou x by dou v, dou y by dou u, dou y by dou v, which is nothing but dou x by dou u into dou y by dou v minus dou x by dou v into dou y by dou u. So this determinant is called the Jacobian of this transformation T. Okay, that is the transformation T is actually we are changing the variables x and y to u and v. This is y actually. Okay. Okay. Now the Jacobian of the inverse transformation T inverse is denoted by dou of uv divided by dou of xy, which is defined as the 2 by 2 determinant dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y. Okay. Now, if the inverse of the transformation T, that is T inverse, exists, then we have the properties that the Jacobian of T into Jacobian of T inverse is equal to 1. Okay, that is the product of the Jacobian of transformation and Jacobian of its inverse is equal to 1. Okay. Now we can discuss an example. Find the Jacobian of the transformation x is equal to r cos theta and y equal to r sin theta. So here change of the variables is from x comma y to r comma theta, right? So the Jacobian of the transformation is given by dou of x comma y divided by dou of r comma theta, which is equal to dou x by dou r, dou x by dou theta, dou y by dou r, dou y by dou theta. Okay, which is equal to we know dou x by dou r is nothing but we have x is equal to r cos theta, so dou x by dou r is cos theta, and dou x by dou theta is equal to with respect to theta we have r is a constant, so minus r sin theta, derivative of cos theta is minus sin theta. Okay, now dou y by dou r is nothing but sin theta, and dou y by dou theta is equal to r into cos theta. Okay, so this is equal to r cos square theta minus minus, that is plus r sine square theta, which is equal to r. So taking r outside we have cos square plus sine square, which is equal to 1. That is the Jacobian is nothing but r. Okay, so you can just verify that the inverse, the Jacobian of the inverse transformation, that is nothing but dou r theta divided by dou x y is equal to 1 by r. You just verify this. Okay. Next, change of variables in double integrals. Okay. So if f is continuous on R, on a region R, then the double integral over R f of xy dA is equal to double integral over S f of uv g of uv into the modulus of the Jacobian determinant. This is the modulus of the Jacobian. Jacobian is nothing but dou of xy divided by dou of uv. This is the Jacobian. So here we need the modulus of the Jacobian determinant, or it can be written as j of uv. Okay. That is, if you have a transformation x is equal to f of uv and y equal to g of uv, then the variables of this double integrals can be changed as double integral over r f of xy dA is equal to double integral over s f of uv comma g of uv into j of uv dA dash. Okay, that is j of uv is nothing but the modulus of dou or the Jacobian matrix, that is dou of xy divided by dou of uv. Okay, where s is the region in uv plane corresponding to the region in r, because we have this is dA is dx dy. Okay, dx dy, so this is the integral of f of xy over the region r. So we are changing this integral or the variables x and y into the variables u and v. So the integrand will be changed, and the region is also changed. Okay, so this S is the region in UV plane corresponding to the region R in XY plane, right? And dA dash is nothing but it is either dx or sorry du dv or dv du, as in this is dA is equal to dx dy or dy dx, right? Changing of the double integrals into polar coordinates is an example of the change of variables in double integrals. Okay, because that is we have a conversion of the rectangular coordinates xy into the Cartesian coordinates r theta by x is equal to r cos theta and y equal to r sin theta. And we already discussed here that the Jacobian matrix is dou x comma y divided by dou r theta is nothing but r. Okay, therefore from this integral we can write this integral over double integral over r, uh, double integral over r f of xy dA can be expressed as double integral over some region f corresponding region s in polar plane or r theta, in r theta plane. F of f of x can be written as r cos theta, y can be written as r sin theta into dA. That means here we need to multiply this. We already discussed that the Jacobian matrix is Jacobian determinant is R, so the modulus of R, that is R itself, into dA is du dv. Okay, that is what is we used here. Dv or dA can be replaced by R into du. Sorry, this is not dr d theta, right? Dr d theta by the the conversion of rectangular coordinates into polar coordinates. We used dA equal to r dr d theta, right? That is which is because of this Jacobian determinant, right? So as an example we can do this. Change the variables in the double integral. Integral from x varies from 0 to 2 and y varies from x2 square root of 8 minus x square 1 by 5 plus x square plus y square dx. So here we can use actually our region is actually a part of a circle, right? Or a sector. That is here the variation is nothing but x varies from 0 to 2 and y varies from x to y equal to square root of 8 minus x square, right? Y equal to x is nothing but the line like this is y equal to x, and y equal to square root of 8 minus x square is nothing but y square is equal to 8 minus x square, that is x square plus y square is equal to 8, which is a circle with center at origin and a radius square root of 8, right? So what will be that circles? That circle will be like this, and this is the line y equal to x. Okay, since x varies from 0 to 2, so we have the point 2 here, and therefore corresponding value will be y square is equal to 8 minus 4 when x equal to 2, that is y equal to 2. So this point is 2 comma 2. This is the line y equal to x, and this point is 2 comma 2. So our region will be x varies from 0 to 2 and y varies from x to this circle. Y varies from y equal to x to y equal to this circle, that is this is the required region, right? So this will be our region. Now we have this circle is a circle with the radius square root of 8, right? And center 0 0. Okay, so if you want to do this or integrate this function, it is better to convert into polar coordinates. So we have the change of variables equations. X is equal to r cos theta and y equal to r sin theta. So from this we already obtained that the Jacobian matrix is dou xy divided by dou r theta is equal to r. So the modulus of this also, modulus of r is equal to r. If you are taking r is greater than or equal to 0. So here the corresponding variations of r and theta will be r varies from 0 to square root of 8, and theta varies from this is y equal to pi, y equal to x, that is theta varies from pi by 4 to pi by 2, right? That is, also we have r varies from 0 to root 8, and theta varies from pi by 4 to pi by 2, right? So this region is our r, which is in xy plane. This is x axis and this is y axis. So this is in xy plane. Now the corresponding region in uv plane is this. If this is u and this is v, the corresponding region to this region r is nothing but u varies from sorry, this is r theta, that is r theta plane. So r varies from 0 to root 8, is r varies from 0 to some root 8, and theta varies from pi by 4 to pi by 2. If this is pi by 4 and this is pi by 2, theta varies from pi by 4 to pi by 2. So this will be the corresponding region, yes, in r theta plane. Okay, so this region is transformed into or mapped into this r is mapped into this region s. Okay, so actually in the region r comma theta, in the coordinates r comma theta, we are integrating with respect to this s. Okay, so this integral can be expressed as this integral 1 is nothing but changing the variables. We have this is equal to this integral is equal to the variations of theta from pi by 4 to pi by 2, sorry, yeah, pi by 4 to pi by 2, and r from 0 to root 8. This is our integrand 1 by 5 plus x square plus y square. We know that x square plus y square is equal to y equal to r sin theta. We have this is r square into modulus value of the Jacobian determinant is r. So r dr d theta. Okay, so this is uh, the change of the variable in this equation. Okay,